Alright, so this is like take 18. We're going to try this, alright? We're going to talk a little bit about resonance. Now here's the thing. We're actually breaking a little bit, we did learn about resonance in Gen Chem, but let's think of bonds in terms of what we know finitely in Gen Chem, right? Which is that if I have two hydrogens over here, I have a total of two valence electrons that can be shared, among these two species. And what we end up with are two electrons that we definitively know are contained in these bonds. That is to say, these electrons are localized in this bond. And so let's take a look at this over here. Let's come in with the core assumption that, we've taken only a little bit of chemistry, so we don't know a whole lot, alright? What we see here is the, I believe, acetate anion, okay? So we have a negative charge on this oxygen. Now, we know for a fact, and this is very simple, okay, that electrons, are negative. So, this is going a little bit ahead of ourselves, okay, but what this tells me is that if electrons are negative, if I see a negative charge, right, that means that, there's a large concentration of electrons, especially strong in that particular area, okay? Now I'm going to be very specific here. I'm going to say that this over here is oxygen A, and this over here is oxygen B. And if we were to take a look at this, we would say, alright, well, here's one structure we're looking at. And if I were to guess between these two oxygens, which one has more electrons, I would probably say oxygen B. The reason being is that I have a negative charge right over here. And so I would predict that, yes, I would see more electrons here on this oxygen than I would on this oxygen. If I were to also guess, let's see, alright, maybe these two carbons, I don't know, which one might have more or fewer electrons. I don't have any, express charges on there. So I'm actually not so sure what's going on. So let's say I run this through a magical computer, okay? And what the magical computer tells me is where the electrons are concentrated in this molecule. So what I find is that, let's pretend like this is the kind of electron cloud, is that it's kind of normal around this CH3. I write it H3C, so that way I show a bond directly to this carbon, but it's the same as the CH3. In any case, what I find is that it's normal around CH3, it's slightly less around this carbon, and then I want you to kind of imagine that I'm, continuing on this cloud up and down, but it's kind of big around this oxygen, and it's kind of the same around this oxygen. I want you to imagine that both of these lows are, approximately equivalent, okay? So what we're shading in over here is actually where the electrons are, okay? Now this is, kind of a flawed little way of doing it, but I like to use this in order to illustrate a point, which is that we predicted over here that we would have more electrons on this oxygen, and that this oxygen over here would not have as many electrons simply because this has a negative charge, that has a positive charge. But what we find is that in the overall hybrid, these two oxygens are roughly equivalent in the number of electrons they have. And moreover, this carbon over here, for some reason, has fewer electrons than that carbon. And so it's obvious then that this one structure alone is not adequate to describe the overall behavior of this molecule. And thus, we need to talk about it using multiple structures. In this case, we're going to show them in resonance. Another way to think of it is that whereas the bonds were over here, and we had, electrons, and they were definitely in this bond. Well, we're putting in a big assumption there. They're definitely in that bond. In this case, we're not going to see the same thing, in that these pi bonds over here, or rather this one pi bond, which again is a double bond, right? You have a sigma and a pi bond. If you had two pi bonds and a sigma bond, you'd have a triple bond. But these electrons here are not stuck in this location. In fact, they're spread out. They're spread out kind of over this whole area. And let's find that out, okay? So the first resonance structure, believe it or not, is the exact structure we just drew above. So a CH3C double O over here, and we have a negative charge. What we end up with over here with this resonance structure then is that we can say, alright, well with resonance, we're typically switching between a pi bond and a lone pair of electrons. So when I'm always looking for resonance, what I do is that I usually try to find a carbon or some species that has a double bond or lone pairs. And I try to think, how can I turn that double bond into a lone pair, or how can I turn that lone pair into a double bond? For me, it's easiest for me to think of this as a push and push, okay? So let's say, theoretically, we were to take these lone pair here, and turn that into a double bond to this carbon. What would happen is that we would break the octet rule on carbon, but we can prevent that by taking this double bond and bringing it up to this oxygen. Sorry, allergies. In any case, when I do this, alright, I end up with a structure that looks like this. Oh, dear. Alright, and what we find here is that my negative charge has moved to oxygen A, and that I now have a double bond to oxygen B, whereas before the double bond was to oxygen B, and my negative charge was on, my double bond was on oxygen A, and my negative charge is now on oxygen B. So that's all nice and good. Here's another structure that's roughly equivalent. What I can do now is, I'm going to ask the same question. How can I turn a double bond into, how can I turn a pi bond into a lone pair? Or how can I turn a lone pair into a pi bond? In this case, what I'm going to do is, if I were to bring this down here, okay, if I were to bring this lone pair down as a double bond, and then move this out, I would have the same structure that I had here. So let's try something a little different. Let's take this bond here, and move it to that oxygen. If I do that alone, it's obvious that I'll be breaking the octet rule on the carbon. But here's the thing. The cardinal rule for the octet rule is that you don't have more than the octet. But sometimes you can have fewer than that octet. And so, in this case, sorry that my hand is so shaky, what I end up with here, and don't worry, I'm almost done. Oh shoot, my hand is shaky. Is that I end up with two negative charges, one on this oxygen here, and one on this oxygen here. Remember how to do your formal charges, right? But then I end up with a positive charge on that carbon. So when I take a look at these three structures here, and keep in mind, all I did was try to find a lone pair that could become a double bond, and then I moved any double bond that would have otherwise broken the octet rule, okay? Is that I find that I have a negative charge here on the oxygen in this structure. Here, I have a negative charge on this oxygen. And then finally, in the last structure, which is pretty horrible, by the way, I have a negative charge on this oxygen, a negative charge on this oxygen, and a positive charge on this carbon. Now, the thing is that I can say that these three pictures, alright, each depict a little bit of this story. And in fact, it tells me a little bit, like, for example, I can have a negative charge on oxygen A, and that's shown here by this increased density. But here's the thing. The electron density here is worlds larger, right, in terms of the increase shown by the negative charge, than the positive charges in that carbon, right? Because if we had the same thing, right, if I had actually had a negative charge here that was equal to that positive charge, then this positive charge should have been really tiny. In fact, it should have probably been as small as these two are gigantic, but you can see that these are much bigger than the dearth of electrons around that carbon. Sorry, I'm really fading now. And so, when I think of this, what happens is that even though I have three structures, and they each tell a little bit of the story about what the overall behavior of the electrons or around this molecule is, the fact is that it's not 1/3, 1/3, 1/3. All right. In fact, I'm going to show you that these two over here, they tell kind of the same amount of the story, but each one of these tells more of a story than just that. And the reason for that is going to be found on page 13 to 14 in the CP book. That's your chemical principles book, right? That's the one that's written by Boykus. Sorry, I'm really out of it right now. Benadryl, I guess, does that to you. In any case. So, one of the rules that I'm given, actually the number one rule, is that the most important structure has the most number of bonds. Sorry, this is so shaky. Again, I'm fading. So, if I'm basing it on that criteria alone, what I see here is I've got, well, I'm going to have 3 bonds here, because CH, CH, CH. So that's 3, 4, 5, 6, 7. 6, 7, okay, so 7 total bonds, okay? Here, I'm going to have, again, 7 bonds. You can count that out, and you'll see exactly what I mean. 3, 4, 5, 6, 7. But here, I've got 3, 4, 5, 6 bonds. So 7, 7, 6. So that automatically, I'm going to put a little X here to show that it's a little worse than the other two. That already shows me that even though these two have equivalent number of bonds, this third one over here has the fewest. And so of the three of these, this one is the least important. The second thing is that we're going to look for charges, which means that basically, more charges you have, the worse this is. Now, what's interesting is that the acetate anion, we already knew it had a -1 charge. If we look at this, we see only one negative charge. So that's a -1, that's good. This is the same thing. But over here, if we were to take a negative, add 1, and then do a negative again, we'd end up with -1. So overall, this is still a -1 molecule. So, the thing here, wow, okay, I am falling asleep. I'm trying my best, guys. The thing here is that the more charges I have, the worse the structure is. So here I have 1 charge, here I have 1 charge, but here I've got 3. Which means that these two have the same number of charges. That has the most number of charges. That's another X against this structure. The third one is not so important right now. It's going to be the electronegative atom has a negative charge, which means that if you have a negative charge anywhere on the molecule, preferably, you'd have it on the you'd preferably have it on the most electronegative atom. So in this case, what we're going to do is we're going to look at the periodic table. And if this was a table, your more electronegative atoms would be found in the top right. And so in this case, the oxygen is going to be the most electronegative. In each of these cases, we see a negative charge on the oxygen, so to be honest with you, 3 is kind of fulfilled. We're nice and happy with that, alright? And, geez, all of a sudden I'm having trouble with the 4th one. But in any case, look that up. This is where you'll find it. So when we look at these, alright, what we find is that this structure over here is by far the worst structure, alright? These two are pretty good. Now, it doesn't mean that this structure doesn't tell us a story, though. In fact, it told us that that carbon, little bit of the time, has a positive charge. And so we show that because, again, electrons are negative. So if we have a positive charge somewhere, it means that there's a dearth of electrons. There aren't so many electrons. And so we actually show that using the density over here, that in fact we have fewer electrons around that carbon, but just a tiny bit. Whereas over here, the negative charges on the oxygen represented big, vast increases in the number of electrons that I had. And that was shown by the fact that both of these structures are, to be honest with you, they're kind of the same. But they also show that these are huge contributors, whereas this is not. And that's it.